So I wanted to do a little video about relative motion. A lot of times we have to rush through this, and it's kind of fun to be able to do these problems. My first example here is for relative motion in one dimension, which is really very simple. We can usually figure it out just through instinct. But then when we want to extend it to 2 dimensions, things can get a little bit confusing, and so then I want to go over that and then do an example. So first of all, in this example with my lovely drawing, we have a person in a truck. The truck is moving at a speed of 15 meters per second. We label that as the velocity of the truck with respect to the ground. Notice there's also a person outside of the truck who's watching. He's smart because he doesn't stand up in the back of a pickup truck. Anyway, this guy is standing in the back of the moving pickup truck and he's going to throw a ball. Now, when he's looking at the ball, his frame of reference is the truck. Like, everything that he views is really from the point of view of being in the truck that's moving. So when he's measuring the velocity of the ball, it's with respect to the truck, and it's 8 meters per second. But the stationary observer would measure the velocity of the ball relative to the ground because that is his frame of reference, the ground. Now, if I ask you how fast this stationary observer would be measuring the speed of the ball, I think that you would probably easily say, well, I would add the 8, which is the speed of the ball with respect to the truck, to the speed of the truck with respect to the ground, because you know that, when you're in the truck, you're moving with the truck, so the ball won't look like it's going as fast as it does from someone standing outside of the truck who sees both motions adding together. So the velocity of the truck of the ball with respect to the truck plus the velocity of the truck with respect to the ground will give us the velocity of the ball with respect to the ground. And so that ends up to be 8 plus 15, which equals 23 meters per second. But I want you to sort of look at how we've labeled these, because I think there's a little trick that can help you out when you're trying to figure out how do I add these speeds together if you get confused. Notice that the truck is sort of located in both of these terms, but it's sort of on the inside. And so we can almost think of those as canceling out and giving us then just the velocity of the ball with respect to the ground. Just something that might help out. So now I want to look at this situation in 2 dimensions. And we're not going to sort of look at a specific scenario at first, but draw it using 2 different coordinate systems. So imagine that I have a coordinate system here, an x and a y and a z, and I'm going to call this coordinate system S. S is a stationary frame of reference. So I use that abbreviation frame of reference because it's a lot to write. And then there's this other frame of reference that's moving with respect to the stationary one. And so I'm going to draw that one here. And we'll just label the axes with primes to represent the fact that it's a different frame of reference. And we'll call this S prime. And S prime is the moving frame of reference. Now we're going to locate a point P. So right now we're going to look at positions, and then from that get a relationship for relative motion. So I can measure point P with respect to 2 different origins. I might measure it, the point P with respect to S prime, or I might measure point P with respect to the stationary frame of reference. And then finally, well, how do those two compare? The other piece of information I need to know is the position of the moving frame of reference with respect to the stationary frame of reference. Now, my vectors are almost overlapping. That's just unfortunate the way I positioned them. But in the end, what we're finding is that the position of point P with respect to the stationary frame of reference, in which I have a prime here, and that doesn't belong there, so let's get rid of that. That was a mistake. Is equal to the position of P with respect to S prime plus the position of S prime with respect to S. And then that makes sense if you think about it. Because, and also when I look at the vectors, the vector or the position of point P measured in this moving frame of reference is shorter, and you need to add the distance or the vector that goes between the two frames of reference, and then finally completing the polygon is the position of point P with respect to the stationary frame of reference. And that's what we have here. Notice once again, I have those two S primes. In a sense, I can almost think of them, or at least this is what I like to do, think of them as canceling out. And so when I add these two together, I end up with the position with respect to the stationary frame of reference. If I take the time derivative, I get then the velocity of point P measured in the stationary frame is equal to its velocity of point P measured in the moving frame plus the velocity of the moving frame itself. Okay? And notice in the end, our first example with the truck and the ball, everything was in one dimension, but the relationship was really the same. The speed with respect to the ground was equal to the speed with respect to the moving frame of reference, which was the truck, plus the velocity of the moving reference frame, which was the truck. So this is the same example or same sort of format, and it makes sense if you really think about it. So we're going to use that to solve a problem and see how we do that when we have to look at this type of problem in 2 dimensions. And so our example is going to be, as it often is, I find that these relative motion problems, basically there's 2 different things that you usually are asked to think about that are changing the motion. One is the wind, and the other one is the water. So you either have like a boat moving in a moving river, and you're trying to figure out different speeds, you know, how it's moving with respect to the river or the shore. Or you're talking about wind speeds and how they affect the motion of an object. And so our problem that we're going to look at for an example has to do with wind speed. And there's a couple other little tidbits within this problem that I want you to think about, or just to notice. Okay, so our cyclist is moving at a speed of 15 kilometers per hour. And he's traveling southeast. Now he feels wind from the southwest, and according to him, the wind is blowing at 25 kilometers per hour. So I want to try to attach some variables or names or descriptions to this that I could use in my expression for relative motion. So this is the velocity of the cyclist with respect to the ground, is 15 kilometers per hour, but it's southeast. So that's a direction. And that means that he's going two different directions at once. If I think about this, north, south, east, west. When we say southeast, we mean directly between south and east, so it's an angle of 45 degrees. And so we're going to have to take that angle into account in a moment. Now the wind, he's feeling the wind at a particular direction and speed. So that's the velocity of the wind with respect to the cyclist, because that's what he's perceiving. And he's saying it's coming from the southwest. So this is the wind, and again, because he's talking about southwest, it's 45 degrees. But notice it's from the southwest, so it's going to be pointing in that direction. And so the question is from the point of view of a stationary observer, what's the speed and the direction of the wind? What I'm asking for there is, what is the velocity of the wind with respect to the ground? Okay? So what we have is the velocity of the wind with respect to the cyclist plus the velocity of the cyclist with respect to the ground is equal to the velocity of the wind with respect to the ground. So I want to write these two velocities in unit vector form. So I'm going to write the velocity of the cyclist with respect to the ground is going to be 15 times the cosine of 45 in the I hat direction, which is east, minus 15 sine of 45 in the j hat direction, which is south. The velocity of the wind with respect to the cyclist is 25 kilometers per hour times the cosine of 45 times I, plus 25 times the sine of 45 degrees times j. I know that the sine and the cosine are the same, but just to kind of think about how we would sort of represent those, I wanted to be consistent. So if I use the numbers here, just to let you know, this would be 10.6 I minus 10.6 j. And the velocity of the wind is 17.7 I plus 17.7 j. If I add them together, literally I have this plus this, which is going to be the velocity of the wind with respect to the ground, is going to be 10.6 plus 17.7 I plus 17.7 minus 10.6 j. That gives me 28.3 I plus 7.1 j. So what it's saying is that when I combine those two together to see what the velocity of the wind is, it's going to be has a lot more x than it has y. So it might look something like that. And what I'm interested in is how big that vector is. I'm interested in its magnitude, and I'm interested in its direction. The magnitude of this vector can be found by using the Pythagorean theorem. And I find it has a speed of 29.2 kilometers per hour. And then to find the angle is the angle whose tangent would be the y component over the x component. And that angle turns out to be 14 degrees. Now, because we've been talking about north, south, east, west, the proper way to measure that is I would say that that's 14 degrees, because it's 14 degrees up from the east direction. I would call that 14 degrees north of east. All right? So I hope that this makes some sense or helps to see how we might do one of these relative motion problems. I think the most important thing is to be able to find the relationship right here. And remember, you can sort of use the fact that you want these two inner, we kind of think of them as inner labels, will sort of cancel out to give us what the two vectors together add up to be. All right, so